No. Got it. Yeah.
Okay, so I am very pleased to have Professor Carsten Rott from the University of Utah as our seminar speaker today. So he is working on, he's joining what is it, IceCube, JSN square, telescope arrays, and cosine collaborations. So today he's going to talk about very interesting, new phenomena with the high energy neutrinos. So please.
Yeah, thanks, Dogen. Thank you very much for the invitation. And yeah, today I'm going to talk about new phenomena with high energy neutrinos and our search for cosmic accelerators at the geographic South Pole using the IceCube Neutrino Telescope. And with the talk today, I will give you an overview where we stand with the IceCube detector, with detecting high energy neutrinos, and then how we can use them to look for new phenomena. So this is the okay. So this is the overview of my talk. So first, I'm going to start introducing neutrino telescopes and IceCube. Then go over some selected searches, in particular search for high energy astrophysical neutrinos, and then looking for a new phenomena with these, and then give you an outlook in the future in our plans for how we want to expand the detectors or next generation neutrino detectors. And in the background here, you can actually see this is actually the South Pole marker, 90 degrees south. This is actually where the geographic South Pole is located. So if you walk around here, you walk around the world. Not everybody has done that. So, so I will tell you also why we are going all the way to the South Pole to build neutrino telescopes there. And so let me start with the main motivation, actually, why we have built the IceCube neutrino detector. And to that extent, actually, we have to go back to the beginning of the last century and going over the cosmic ray mystery. So as you know, more than 100 years ago, people observed that there's ionizing radiation, and it's not really clear where this ionizing radiation is coming from, if it's coming from Earth, from radioactive decays, or if there is some radiation coming from space. And this was eventually solved by Victor Hess, and you can see him here in one of the daring balloon experiments that he undertook, where he took electroscope basically to high altitudes up to 4 to 5 kilometers. And that, of course, at that time was quite daring experiment because he didn't have any oxygen mask or so. So it was also some substantial risk to his life. But he was able to prove actually that ionizing radiation is increasing with altitude, and therefore showing that there is ionizing radiation coming from space. And this is actually the picture how we understand it today. High energy cosmic rays enter the upper atmosphere, provide light in the atmosphere, and generate cosmic ray air shower. And these remnants from the cosmic ray air shower is what Victor has detected. Now, we can measure these cosmic ray air showers today in great extent. For example, with a telescope array detector that is located near Delta, Utah. And there we have more than 500 of these scintillation surface detectors in combination with fluorescent detectors that observe these cosmic ray air showers. Now, today I don't want to talk much about how this exactly works. I want to more go into what we have actually found using these cosmic ray air shower detectors. And we have measured quite precisely the cosmic ray spectrum. And the interesting part of the spectrum is that it extends basically from a few GeV up to energies of 10 to the 10, 10 to the 11. So eta electron volts, and these humongous energies actually have, if you basically put these are essentially fixed target experiments, like where you have the cosmic ray colliding with basically atoms or in the atmosphere. If you translate it to the collision energies at colliders, these energies are far beyond this. And so the big question that we all have is actually, where do these particles get accelerated? Where do they come from? And the difficulty in solving this puzzle, where the high energy cosmic rays are coming from, basically goes back to this first observations to Victor Hess. And the problem, of course, even though we observe these high energy cosmic rays, finding their sources is so difficult because the cosmic rays get scrambled in the galactic and extragalactic magnetic fields, and therefore we cannot correlate the observed cosmic rays with any sources, or it's extremely difficult. I mean, there are actually some indications that for the nearby sources, something might be emerging, but that's a different story. So now neutrinos can help actually finding the sources of the high energy cosmic rays, because at these cosmic accelerators, and I have a generic accelerator shown here, where we have jets in which hadrons get accelerated, and if these hadrons interact, they produce pions, and when pions decay, they give us neutrinos. And since neutrinos are weakly interacting, they directly travel to us, and they don't get deflected or attenuated in any significant way. So therefore, detecting high energy neutrinos will allow us to also find the sources of the high energy cosmic rays and solve this long-standing puzzle where the highest energy accelerators in the universe are located. Now we can now we just have to detect these high energy neutrinos. The easiest way to detect a high energy neutrino is via their interaction. If you have a charge current interaction where you have a neutrino coming in interacting via W boson exchange, you generate the corresponding lepton. In case of a muon neutrino, as it's shown here, you generate then relativistic muon, and if this muon travels through water or ice, it will send out a cone of strength of light, and we can detect this light and with a precisely timed sensor, optical sensor ray. Now this approach has been taken by a number of experiments around the world, and give a summary of them here. The currently operating and planned large volume neutrino detectors. So we have, and so we have basically Super Kamikande detector, which is a 22.5 kilodon fiducial volume neutrino detector, using several 10,000 PMTs that monitor this volume. This has, of course, a very low energy threshold, but if you want to detect high energy neutrinos, you need a very large detector to make up basically what neutrinos basically lack in interaction cross-section by volume of the detector. So the best way then is to use a naturally occurring medium that has good optical properties, and for that we can use water in the ocean or lakes, and this all has been done. For example, with Lake Baikal experiment, which uses the fresh water in a lake in the Mediterranean Sea. We have neutrino telescopes being constructed. A Taurus detector has been running there, and Ames 3 Net is currently under construction there. And by far the largest detector is the IceCube Neutrino Telescope located at the geographic South Pole, where we have implemented 1 gigaton of volume of the Antarctic ice with more than 5,000 optical sensor modules. And you can see a picture here at the completion of the detector construction, actually in 2009. And there's also, it's a little bit cut off, but there's also champagne on ice here where we're celebrating when we completed the detector. Now let me just show a simulation here of how this Cherenkov light looks like when a high energy muon passes through the detector. So in this simulation, you can see strings of optical modules. These dots indicate that there is a module, and whenever the light, Cherenkov light hits one of these modules, we mark this by these blobs, and the sizes of the blob indicate how many photons were detected, and then the color indicates the timing when this occurred. And then based on this hit pattern, you can reconstruct the event. And let me just play this one more time so that you can see this clearly. Okay, let me introduce the IceCube detector in a bit more detail. So the IceCube detector is located at the geographic South Pole. This is actually an aerial view of the geographic South Pole. The Amundsen Scott South Pole Station is located here, and then the detector is basically just a kilometer away from the geographic South Pole. And then very below the surface of the ice, and I will show some more details about this detector. Also, the IceCube collaboration now consists out of more than 50 members from around the world, and I just indicate places where I've been from one university since 2013, and then recently when I moved to University of Utah. And let me just skip this. I showed this already. So the IceCube detector consists out of more than 5,000 optical sensor modules that are buried below the surface of the ice. At the depths between 1.5 to 2.5 kilometers, we have these 86 strings that are separated essentially by 125 meters. 7 of the strings are more closely arranged as in this configuration of the deep core detector, which gives us a lower energy threshold where we have about 10 GeV. For the IceCube detector, we have more like 100 GeV. And then we use these optical sensor modules that's shown here. Okay. As for the research program that we are performing with IceCube detector, it's extremely diverse, covering different areas of science, from astrophysics to atmospheric science to particle physics and cosmic ray physics. And also this diversity in science is also reflected in the diversity of our collaboration. Now let me actually start jumping into the science and starting with the search for astrophysical neutrinos and give you some of the latest results here. So when we search for astrophysical neutrinos, we basically have to apply different search strategies in order to distinguish an astrophysical signal from atmospheric backgrounds. So just to give you a sense of scale, we detect about 100,000 atmospheric neutrinos per year, and only a few of the neutrinos that we detect are of astrophysical origin. So we have use statistical methods to distinguish them. So the different methods that we have been applying is basically search for point source. So basically a clustering of neutrinos on the sky, transient source searches, where we look for a short timing coincidence of the neutrino signal. And multi-messenger searches where we look for correlation of neutrinos with other particles like gamma rays, or for example with gravitational waves. And then also we can look for deviation of the expected spectrum from the atmosphere that would indicate that there's some excess from astrophysical neutrino event. And because we expect that the atmospheric neutrino spectrum is basically deeply falling, while typical astrophysical neutrino or acceleration models predict a flux that has e⁻² spectrum roughly. Now, the first indication of an astrophysical flux came actually via two very exciting events. I show one of them here, and Rott, which was a 1 PeV event. That was the first indication actually of an astrophysical neutrino flux. We have since then measured this flux in much greater detail and observed basically a diffuse astrophysical neutrino flux based on the spectrum, and this is basically shown down here. So we have basically the atmospheric muon backgrounds, atmospheric neutrino backgrounds, and then this additional component we can link basically to the astrophysical flux. We also recently observed an exciting event at an energy of roughly 6 PeV, and this was associated with an glass shower resonance event. So in this case, you have an electron antineutrino interacting basically with an electron, and this is expected to happen roughly at 6 PeV. This is one of the candidate events that we observe.
Can you go back something?
Yeah, sure.
So let's start off. Those are IceCube sources?
Right. So these are not sources, but these are events that we have detected in high energy neutrinos. So and they can be pointed back to a specific location in the sky. But these events or this sky map doesn't show any significant clustering or correlation with any specific sources.
Okay, so these bright points don't have spatial coincidence with any astrophysical sources?
Right. I mean, this thing is here that since the astrophysical or the neutrino signal is not really attenuated, so they can come from very high or redshifts. So therefore, you have actually a lot of potential sources. So for each neutrino, you could speculate about the number of potential sources. Yeah. Okay. Any other questions? Okay. And please feel free to interrupt me at any time. So, okay. Now, when we measure this diffuse astrophysical neutrino spectrum, this is actually indicated here by these green crosses. We also can measure different type of events in our detector corresponding to different topologies, and those correspond then to different type of neutrinos. So we can measure these outgoing events, which is dominated by muon tracks. So muon neutrinos, the diffuse events that I showed earlier are dominated by electron neutrino and neutral current interactions, and all of them actually give us a consistent picture that we basically this diffuse astrophysical neutrino flux here. And this is one of the beautiful things about IceCubes, that you can use one detector and independently perform several measurements using different type of event classes, and all of them basically lead to the same conclusion that you have this diffuse astrophysical neutrino flux. Now, more interestingly, let's actually look now for sources of these neutrinos. So the first indication of an astrophysical neutrino source, or high energy astrophysical neutrino source, actually came in 2017 and part of a multi-messenger observation. So whenever we observe a high energy neutrino event, we send out an alert so that other observers can look at the location where we detected this high energy neutrino. So in 2017, we detected a 270 TeV event. This is actually shown here in the event display, and we can point them back with degree precision. And whenever we detect such a high energy event, we send out an alert. This is actually the kind of pipeline here. We first do a fast processing at South Pole, then send the data to the north, and then basically send out an alert as part of a GCN, and then other observatories can basically look at this. Takes roughly 33 seconds on average for this alert to be sent out. Doing a precise reconstruction of these events can be very can take a lot of computing time. So recently also we made a lot of improvements by using machine learning for the reconstruction of these large events, which actually reduces the uncertainty ellipse and gives more reliable position. Also, these alerts you can receive on your cell phone, actually as part of the IceCube AR, the augmented reality, and you can display events. So this is actually like one example where I'm displaying such an event in my office. And yeah, so with this event, with this 290 TeV event, we were able to point it back basically to within this uncertainty ellipse. And when we had sent out this alert, also Fermi and Magic basically looked at this location and saw the flaring laser at this location. Now, the probability that basically Magic and Fermi would observe a flaring laser at this location is extremely unlikely, and we basically found this is like roughly a 3 sigma effect. Now, since we found this location, we also have now a hypothesis to test basically for astrophysical neutrino source. So and this is basically where this first 290 TeV event came from, and we can we actually went back in our archival sample and looked in our archival data, and we found that there was prior to this event in 2019, we also had a burst of neutrinos actually during 2015, and the significance of this burst is 3.5 sigma, which is independent of the 3 sigma. So you can combine the two numbers, which gives you high confidence that there is an astrophysical neutrino source, or that lasers are, that this laser is a source of high energy astrophysical neutrinos. And this is, yeah, just an artist drawing of this laser. Now, recently, this was actually 2 weeks ago, we announced the evidence for a second high energy astrophysical neutrino source, NGC 1060H, which is a Cipher 2 galaxy at a distance of 14.4 megaparsecs from us. And the way this proceeded basically is we looked at our most recent point source map. This is now almost 10 years of data, and what we are showing here is actually the significance at any source location, basically scanning through this sky map and then plotting the local p-value at specific locations. And the highest significant spot is actually at this location of NGC 1068. And then we have also, yeah, two other sources that stick out, TXX 0506/56. This was the laser I was talking about before, and then PKS 1424. This is also a blazer.
You might be like this, like every segment off of your Texas event.
Right. Yeah.
So like, did you just miss that the first time because 3 to 4 sigma bumps happen, frequently enough that you're just like whatever, or is it
Right.
you just kind of ignored it and you just dismissed it as something else? Is that true? Is that fair there?
Right. So the reason why this was not seen before is basically we have an analysis that looks for transient events for basically any any kind of excess of events, but it basically scans the entire sky map and looks for the most significant event on that sky map. And then we only compare kind of, okay, if this most significant event is above any kind of threshold that you would expect from random fluctuations over the entire sky map. So then with that analysis, there was no significant excess found over scanning over the entire sky map. But then once we had this event found, we basically went back and said, now, okay, now let's actually test the hypothesis that neutrinos are coming from this location. So then we looked at this location and yeah, basically ran this analysis and then found, okay, there's this.
And like the widths of the same different. I mean, is the time scales reversed? It's like consistent with each other. Is the time scales consistent with each other? The first. I'm looking at the widths of the curves.
Oh, yeah, no, it's not consistent because so these birds are actually very, very different. So this first bird that was detected was actually detected through the coincidence with the flaring of in gamma rays. But then during 2015, actually, Texas was pretty quiet, so there was no significant flaring observed in gamma rays at the time. So that tells you actually that neutrinos and gamma rays are not necessarily correlated. Because one of the other things that lasers, of course, had always been a potential suspect for astrophysical neutrino sources, and we have done many searches before for lasers, but never observed any significant access. So it tells you basically that maybe there's some subclass of lasers or some. I mean, lasers are basically known that they are very sporadic and not continuously emitting. So it's probably just the type of hypothesis that we tested. So maybe they're different. Yeah, we just have to be more maybe, yeah, test more different hypotheses or look for a subclass of lasers. So then with NGC 1068, we found the most significant clustering of neutrino events actually at this spot. In this region, actually we have this 81 neutrino events, and NGC 1068 is actually located at the location. So there's a very clear correlation and also tend to be in excess of events at this source location. Now again, if you just do the random scan over the entire sky map, overall, the clustering of events here is not that significant, but we had also predefined like a source or a list of 110 potential neutrino sources, and NGC 1068 was one of them. And then basically testing the specific hypothesis with that neutrinos are coming from NGC 1068, then had a significance of 4.2 sigmas. So there's clear evidence that neutrinos are coming from there. And also comparison with gamma ray data and different neutrino models from neutrino emission from AGNs. This actually, the observed plots actually fits quite well to these theoretical predictions. Now, the most interesting part is actually if we now compare the diffuse astrophysical neutrino flux that we have observed with the fluxes from Texas and the NGC 1068, you can see that there's actually 2 orders of magnitude between them. So actually this plot actually is by phase by 2 orders of magnitude, which is of course important. That tells you that these 2 sources alone don't really account for the diffuse astrophysical neutrino flux that we have observed, and that there should be many more sources. Many of them we might not be able to resolve, but there's room for potentially many more. Yeah. One of those potential sources is maybe tidal disruption events. So there was also a report of an coincidence of a tidal disruption event with basically with the observation of high energy neutrino. Now, these 2 neutrino events that we observed or that we linked to astrophysical neutrino sources, I want to put them kind of on a distance map here. So actually, NGC 1068 is rather close to us at 40 megaparsecs, but then TXS is basically at more than a gigaparsec, so redshift of 0.3, and this is actually beyond the reach of high energy cosmic rays or gamma rays or even the sensitivity of LIGO. So neutrinos allow us to really explore the very deep cosmos, and this is maybe also showing some potential neutrino sources and the distance scales of the 2 events or evidence for neutrinos from NGC 1068, and then the observation of neutrinos from TXS. And these basically gamma rays would not be observable in these distances at these energies because they interact with the cosmic microwave background and the infrared background light. Now, since neutrinos travel from these far distances, also the question comes up, okay, is there any effects that we can observe from the neutrinos coming from these distance scales, or new interactions that occur from these distances? Or are there any new physics associated with the diffuse astrophysical neutrino flux that we observe? One of the hypotheses that we want to test, for example, are the signs from any dark matter or dark matter annihilation or decay. And this is actually a hypothesis that one of my students worked on, He's actually on the way to the South Pole now, so he became our new winter over. So he will spend 1 year there. He's now on McMurdo, and then we'll travel on to the South Pole to stay there. But so he looked for a test of the dark matter hypothesis. So if dark matter would decay, you would expect that it be clustered, that you observe a neutrino signal that is clustered near the galactic center, plus you have some component of extragalactic contributions. And we looked at this hypothesis and didn't observe any excess, and were able to set bounds on the dark matter lifetime, and these are the bounds shown here as part of the as function of the dark matter mass and the corresponding lifetime. And the IceCube bounds are by far the strongest one, and then at lower energies you have bounds from Hawk and Fermi. Recently, there was a new result by Lasso, which I didn't put on there yet. I think that's not yet published, but that one also has very competitive bounds as its highest energy. Now, another way that we look for BSM physics with IceCube is actually by looking for energetic neutrinos that are coming from the sun. The dark matter could be captured in the sun, and then through the annihilation of dark matter, we could observe neutrino signals. And in particular, these signals would be very sensitive to spin-dependent nucleon scattering. And essentially, you're probing the same process that we are looking for with dark matter direct detection experiment, where basically the dark matter particle scatters on the nucleon, then loses energy, and eventually gets captured by the sun, where it then accumulates and annihilates, and only neutrinos basically then can make it out of the sun. Now these are some of the bounds that we got here for spin-dependent and spin-independent nucleon scattering, compared to some models, basically a scan of MSSM parameter space, and you can see that the IceCube bounds are some of the most competitive ones. And we recently also improved these bounds by optimizing our analysis separately for low and high energy sample. And in addition, we also included some new electroweak corrections based on this paper by Rott and Weber. And with that, actually, we were able to improve our limits substantially, so that dashed lines are basically the limits that were shown in the previous slide. And these solid lines are improvement. So we were able to improve bounds by an order of magnitude further. Also, potential backgrounds to these neutrinos from dark matter annihilation in the sun could come from cosmic rays interacting in the solar atmosphere. In this case, cosmic rays enter the solar atmosphere, produce a particle shower, and produce pions. When pions decay, neutral pions will give us gamma rays, while charged pions will give us neutrino. And we recently observed a component from gamma rays from the sun. So this was basically based on a paper using public Fermi data. And you can see this is actually a theoretical model prediction for this gamma ray flux from the sun. And then this is by the Fermi collaboration, and this is our analysis actually using here 6 years of Fermi data. And this is actually on the Fermi paper that basically look at the sun and look for two components. One component from inverse Compton scattering, where basically the cosmic gray electrons scatter with the photons from the sun, and basically you have this upscattering result in this component, and then you have a second component coming from the solar disk, where cosmic rays are interacting with the solar atmosphere and producing pi zeros that then decay with this hard component. Now, since this spectrum basically extends into the GeV range, this also makes this very detectable if there were a neutrino component, because IceCube is of course very sensitive to GeV neutrinos. This is an analysis actually Son Jin, one of my students, looked for, and we basically look for any neutrino signal that's coming during the time of the Oslo winter. So basically this period when the sun is below the horizon. And yeah, he didn't observe any signal, but we were able to place the first bound on the solar atmospheric neutrino flux. And then recently, Gerrit Rollinghoff, one of my other students, was able to improve on this. And we also produced differential bounds now. And this is compared to bounds from Hawk. So we have the gamma ray bounds here, the gamma ray observed flux. These are our limits here. And then we have basically the neutrino bound right here. And you could expect that the neutrino flux is actually larger than the gamma ray flux, because the gamma ray flux will of course be attenuated by the solar atmosphere, while neutrinos can actually pass through the sun or the atmosphere. Okay, so lastly, let me give an outlook in the future. What's next? This is a Gen 2 penguin, so that's also the name of our next experiment, generation 2, Gen 2. Now, we're actually working towards a next generation neutrino detector at the South Pole, building on the success of the IceCube experiment. And the first step towards that is actually building an upgrade to the IceCube detector to more precisely measure the ice properties of the Antarctic ice, and to expand the detector through an infill array that allows us to give us access also to GeV neutrinos. Now the plan is to deploy 7 additional strings in the center region of the IceCube detector to implement a volume of roughly 4 megatons. And with that, we will use about 700 additional modules that are improved compared to the IceCube module. The IceCube module basically has a single 10-inch PMC, while upgrade modules will consist of these multi-PMC modules that have 3-inch PMCs, and the DX modules, which have basically 2 large PMC facing up and down. And this will also give us some directional sensitivity to the strength of light that is detected at each individual module, improving then also on the bench reconstruction. Now, these new modules and the new strings will give us additional sensitivity to study neutrino oscillations. This is one of the main science targets here. This is actually a sensitivity for using 3 years of IceCube upgrade data. See, this is actually for atmospheric neutrino oscillation measurements, delta m squared and sine squared theta 3. We are expected to have basically one of the best neutrino oscillation measurements. And I will show you actually the next slide where we are already with IceCube deep core. So we are almost getting there already. So we are already exceeding this. So this sensitivity here is actually something that's very conservative. One of the other main science goals of the IceCube upgrade is checking for the unitarity of the PNS matrix. So basically, if you have 3 neutrinos or any additional neutrino, and this unitarity measurement also be, we have sensitivity basically to measure the tower appearance basically with 10 or 6% precision. Now this is actually a recent update from one of our new oscillation analysis using the IceCube deep core sample, and we have the full sample sensitivity, which is already comparable to those from NOVA and T2K. So we are already reaching almost the goals that we have set for IceCube upgrade. So with IceCube upgrade, we'll actually go beyond what we initially expected. Now, one of the other big improvements that we are doing with the IceCube upgrade is actually deploying new calibration systems. One of these new calibration systems is a camera-based system that will be used to precisely measure the scattering and absorption in the eyes and how light propagates through the eyes by getting photographic images. So we have these developed with camera system where we have an illumination module. So it's basically 1 watt LED, and then we have a high resolution high light sensitivity camera that is integrated with all of the new optical modules that will be deployed. We actually had sent a test system all a few years ago. This is actually Paravoya, who's now becoming the new winter over on his way. Also, when I had sent him to the fall, he liked it so much that he is now spending the year there. This is such an image of this camera. So basically, you have this fisheye lens, which gives you a large field of view. This is during one of our meetings of the collaboration group. We also did a lot of tests with this new camera system. For example, in one of the swimming pools, actually, with my group here, and this is actually in Korea, this Gyeonggi Physical High School. They actually have a 50-meter pool, which is quite amazing. And for high school to have such a big pool, and we use that during the night. One of my students here underwater trying to deploy or test the modules, and then we turned off the light actually and tested these the LEDs and then cameras, and this is like some examples here. So for example, how well we can measure the spatial resolution with these cameras. Now, if we have a perfect understanding of our ice properties, we should be able to substantially improve the reconstruction of the high energy neutrino events. This is an example here of the deposited energy of these neutrino events. So this is basically PDV events here, and this is for electron type neutrino events. And for these electron neutrino events, we have angular resolution of 10-15 degrees. But if we have better understanding of the ice properties, we expect that we can reduce this to less than 5 degrees. So if we can have this substantial improvement in reconstruction of the neutrino events, we can actually go back and use our existing data sample and then retroactively analyze the existing data and maybe make discoveries already by having the improved ice model. So that's why this calibration, new calibration systems are so important. Then lastly, one of the main goals of IceCube Gen 2, this is now actually going towards beyond IceCube upgrade. We want to build actually 10 times larger detector, which consists of 120 additional strings to the 86 IceCube string to implement roughly 10 times larger volume. And with that, we'll be able to more effectively probe individual astrophysical neutrino sources. So this band here shows the diffuse astrophysical neutrino flux. Then these red stars indicate potential sources given by the effective neutrino luminosity and local density. And you can see that all these potential sources sort of line up along this line. So they are consistent with the diffuse astrophysical neutrino flux. But what we really want to understand, which of these sources are responsible for the diffuse astrophysical neutrino flux, or which mix of sources. We know already, since we observed neutrinos from Cypher 2 galaxies and from laser, that there are multiple sources. So answering this question, which other cosmic accelerators will require to improve our sensitivity, and that is basically what's shown here, going from IceCube to IceCube Gen 2. So we'll be able to probe specific astrophysical neutrino sources. Also, we plan to further improve our optical modules. We are looking at these kind of LOM designs, which is an elongated optical module that basically contains 16 to 18 PMPs. And this elongation in the module basically allows us to drill smaller holes and therefore reduce the resources that we need actually to deploy these modules. One of the other things that we're also looking into, and which particular my group has started in Utah now to look at, is actually how we can also reduce the environmental footprint at the South Pole. And we are looking in using renewable energy sources actually for drilling these holes. Currently, we are basically just using kerosene, but we plan to use in future also an array of solar panels. And this is actually not at the South Pole, but this is in the salt flats in Utah, where it looks very similar. Actually, I have also this highly reflective environment, that we use these bifacial solar panels that we basically test to see how they perform. Basically, as you know, a solar panel basically generates DC power, and DC power you can very effectively also use for water heating. So that this is something that we want to include then in our future drill system. Okay, so with that, let me actually end. And so I hope I convinced you that we have entered a new era in astroparticle physics. We have now observed sources of high-energy astrophysical neutrinos as TXS and the evidence from NGC 1068. We can also use these high-energy neutrinos to look for new phenomena, to look for rare interactions, or to look for dark matter and other physics beyond the standard model. We're also on our way to expand the IceCube detector. The next step is the IceCube upgrade, which will be deployed in 2025. And beyond that, we are looking towards Gen 2 and building the next generation of neutrino detectors as a whole. So thank you.
Okay, so questions for Carsten?
So you mentioned we couldn't necessarily determine the neutrino switches from the map, but like how are we able to determine the switch this time for the NGC?
Right. So let me go back to this slide. So we basically had predefined a list of sources that we wanted check. So we had a list of 110 potential astrophysical sources for neutrinos based on gamma ray observations or other considerations. And this source list we had already defined a long time before. And we are basically testing the hypothesis, is there any excess of neutrino events coming from specific locations? If you just look at this heat map, you basically have to correct for trials. So also if you do this, then these significances at the individual spots basically don't reach 4 sigma. They just reach to something sigma or so. So by itself, if you consider all the trials just on this map, these sources wouldn't be significant enough to stick out. But since we are looking basically for excess of events from a specific source list, we can basically say basically that there is evidence for neutrinos coming from this location. Yeah.
So we cannot, so we basically by comparing it to the already existing list, we can determine the source. But like
Right.
since neutrino doesn't really tabulate graphically, we can't really determine the distance and so on.
Right, you cannot determine the distance, and as I said, or as I showed for TXS, this one is at a redshift of 0.3, so neutrinos can come from very far away, so that's yeah, that's very different from high energy gamma rays, because we are of course significantly attenuated.
Just out of curiosity, is there? So when you report the 2 different significance values for the nexus source, those are 2 different peaks, right?
Right, yeah, so this.
Is there a reason you don't do it over the entire lifetime of the experiment, like to the background, does it just accumulate too much within the source? I'm just wondering if you can get a higher significance report it for the entire duration of the experiment.
Right, so we basically this peak here, it would correspond to the 290 TeV neutrino that we observed, the single event. But we use this event to formulate our hypothesis that we have neutrinos coming from this location. So then we have to kind of disregard this when we test it, because otherwise you would be biased if you include or this in your test. So that's why we still show the significance here that it would correspond to just a single event, but when reporting, we report basically the significance of the neutrino alert and the coincidence with the observation in gamma rays, and then out of that we formulate a new hypothesis to check if there was any significant flaring before this event, and that basically then resulted in this 3.5 sigma excess.
So in gamma ray experiments that everybody has this, you can they can look at a pulsating source,
Yeah.
right? But also try and just say overall time, got into account how that would compared to background noise overall time. But I guess the neutrino experiments.
Right, the neutrinos we can also do that, and when you look at this, the overall sky map, the 3 most significant p-values that we have. I mean, the most significant is at NGC 1068, and then the second and third most significant are actually at these 2 lasers. So TXS alone also at this, in looking basically for a continuous source or just integrating over the entire observed lifetime, also gives you already a high significance. Yeah.
What is this significance if you have?
So again, like taking these trial factors into account, this is like something more like a bit more than 2 sigma. But that is basically taking all the cloud factors here into account over the entire skynet.
So other questions?
So what is the event rate in IceCube? How many times observer or trigger event?
Right. Okay.
I have a
Yeah. So we observe about 100,000 atmospheric neutrinos per year. And then from astrophysical neutrinos, these are based on the flux that we have observed. There are a few hundred actually per year in our sample, but most of them are of course hidden. And then our trigger rate is actually dominated by atmospheric muons, so basically cosmic rays, and that basically gives us a trigger rate of 2 kilohertz. So this is the dominant number of events. Yeah. So
Okay, so any further questions? Okay, so if not, let's thank Carsten again.